So far we talk about the oscillation from the mass spring system. It is not the only system that exhibit the oscillation. Now we will talk about the other system that exhibit the oscillatory motion. It is a pendulum. The simple pendulum is consists of a mass M hang with a string, hang on a string like this. Okay, you have a mass M here, and you hang this mass by this string. Okay, the equilibrium point will be this point that the mass M hang vertically like this. And if you pull or if you lift the mass M up a little bit, but still make this string stretch, it means that you have a tension in this string. Okay, so you lift the mass M and release. You know that the pendulum will move back and forth. I mean, the mass M will move back and forth. We can say that it swing back and forth between 2 points. Allow the equilibrium point here. Okay, so the system of mass hang with the string exhibit the oscillatory motion, but this is a different system from the mass spring system, and we call this a pendulum. Okay, now let's see in the detail of the mathematical expression of the equation of motion of this pendulum. Okay. First, we have to look at the forces that act on the mass M. You can see that there are 2 forces that act on the mass M. First is the gravitational force. The gravity. Okay, and the second is the tension. Is a tension in the string. Okay, so if you look at the figure, you can see that we have this mg, which is the gravity act point down vertically, and we have the tension, this, okay, point toward to the pivot point here, to the pivot point here. So the net force act on mass M is equal to mg plus t. Okay, we can resolve the net force into two components. The component along the string, the radial component, and the component along the path of the motion or the tangential component. Okay, so if we look at the radial component first, radial component, okay, you can see that the radial component of F must be 0 because the tension, because the string is not break, and the mass M attached with the spring all the time. So the tension has to balance with the component of the gravity along the radial direction. So we have that 0 is equal to the T minus mg cos theta. Okay, we define the angle theta like this. This is the angle theta. So the component of the gravity in the radial direction is the mg cos theta, and that must be equal to T. Okay. Now look at the tangential component. The tangential component. You can see that we have only the tangential component of the gravity. So we have that Ft is equal to the minus mg psi theta. We use a minus sign here in the sense that we define the positive direction, the tangential, in the tangential direction, that we measure the positive theta in this direction. So it means that if the direction that point away from the equilibrium point is positive, so it means that the direction that point to the equilibrium point is negative. So in this figure you can see that if theta is positive, okay, we have this positive theta, the tangential component of the gravity will be negative. Okay, but if the mass m is here, you can see that this is mg, and we have this theta, and now theta is negative. So you can see that the mg sine theta is positive. Okay. Let's change the definition of positive and negative a little bit. We have to define the positive is not when it's not the direction that point away from the relaxation point, but the positive is the direction that point to the light of the equilibrium point. Okay, so you can see that this is a positive direction. This is a positive direction, and this is a negative direction. So at this point, mg sine theta point to the left. Okay, so it has a negative sign, but in this point, mg sine theta point to the right, so it has a positive sign. Okay, so that is the definition of the positive and negative. So we have the equation of motion, that is Ft is equal to the minus of mg sine theta. But Ft can be expressed as the MAT equal to the minus of mg sine theta, and MAT is equal to the ML alpha equal to the minus of mg sine theta. Here, alpha is the angular acceleration of the mass m. So we may write this equation as ml d square theta by dt square is equal to the minus of mg sine theta, which you can see that m is cancelled, and we have that d square theta by dt square is equal to the minus of g over L sine theta. Here, L is the length of the string. Okay, it's the length of the string. So now we have the equation of motion of the pendulum. We will next solve this equation to get the equation of theta as a function of time.